The High-Frequency Active Auroral Research Program is an ionospheric research program jointly funded by the U.S. Air Force, the U.S. Navy, the University of Alaska, and the Defense Advanced Research Projects Agency. Designed and built by BAE Advanced Technologies, its purpose is to analyze the ionosphere and investigate the potential for developing ionospheric enhancement technology for radio communications and surveillance. The HAARP program operates a major subarctic facility, named the HAARP Research Station, on an Air Force CA-owned site near Gakona, Alaska. The most prominent instrument at the HAARP station is the Ionospheric Research Instrument, a high-power radio frequency transmitter facility operating in the high-frequency band. The IRI is used to temporarily excite a limited area of the ionosphere. Other instruments, such as a VHF and a UHF radar, a fluxgate magnetometer, a digisonde, and an induction magnetometer, are used to study the physical processes that occur in the excited region. Work on the HAARP station began in 1993. The current working IRI was completed in 2007, and its prime contractor was BAE Systems Advanced Technologies. As of 2008, HAARP had incurred around $250 million in tax-funded construction and operating costs. It was reported to be temporarily shut down in May 2013, awaiting a change of contractors. As of May 2014, it has been announced that the HAARP program will be shut down later in the year. HAARP is a target of conspiracy theorists, who claim that it is capable of modifying weather, disabling satellites and exerting mind control over people, and that it is being used as a weapon against terrorists. Such theorists have blamed the program for causing earthquakes, droughts, storms and floods, diseases such as Gulf War syndrome and chronic fatigue syndrome, the 1996 crash of TWA Flight 800, and the 2003 destruction of the Space Shuttle Columbia. Commentators and scientists say that proponents of these theories are uninformed, as most theories put forward fall well outside the abilities of the facility and often outside the scope of natural science. Overview. The HAARP project directs a 3.6 MW signal, in the 2.8 to Euro 10 MHz region of the HF band, into the ionosphere. The signal may be pulsed or continuous. Then, effects of the transmission and any recovery period can be examined using associated instrumentation, including VHF and UHF radars, HF receivers, and optical cameras. According to the HAARP team, this will advance the study of basic natural processes that occur in the ionosphere under the natural but much stronger influence of solar interaction, and how the natural ionosphere affects radio signals. This will enable scientists to develop methods to mitigate these effects to improve the reliability or performance of communication and navigation systems which would have a wide range of both civilian and military uses, such as an increased accuracy of GPS navigation and advances in underwater and underground research and applications. This may lead to improved methods for submarine communication or an ability to remotely sense and map the mineral content of the terrestrial subsurface, and perhaps underground complexes, of regions or countries, among other things. The current facility lacks range to be used in regions like the Middle East, according to one of the researchers involved, but the technology could be put on a mobile platform. The HAARP program began in 1990. The project is funded by the Office of Naval Research and jointly managed by the ONR and Air Force Research Laboratory, with the principal involvement of the University of Alaska. Many other universities and educational institutions of the United States have been involved in the development of the project and its instruments, namely the University of Alaska Fairbanks, Stanford University, Penn State University, Boston College, UCLA, Clemson University, Dartmouth College, Cornell University, Johns Hopkins University, University of Maryland, College Park, University of Massachusetts Amherst, MIT, Polytechnic Institute of New York University, and the University of Tulsa. The project specifications were developed by the universities, which are continuing to play a major role in the design of future research efforts. According to HAARP's management, the project strives for openness, and all activities are logged and publicly available. Scientists without security clearances, even foreign nationals, are routinely allowed on site. The HAARP facility regularly hosts open houses, during which time any civilian may tour the entire facility. In addition, scientific results obtained with HAARP are routinely published in major research journals, written both by university scientists and by U.S. Department of Defense Research Lab scientists. Each summer, the HAARP holds a summer school for visiting students, including foreign nationals, giving them an opportunity to do research with one of the world's foremost research instruments. Research: HAARP's main goal is basic science research of the uppermost portion of the atmosphere, termed the ionosphere. Essentially a transition between the atmosphere and the magnetosphere, the ionosphere is where the atmosphere is thin enough that the sun's X-rays and UV rays can reach it, but thick enough that there are still enough molecules present to absorb those rays. Consequently, the ionosphere consists of a rapid increase in density of free electrons, beginning at 70 km, reaching a peak at 300 km, and then falling off again as the atmosphere disappears entirely by 1000 km. Various aspects of HAARP can study all of the main layers of the ionosphere. The profile of the ionosphere is highly variable, changing constantly on timescales of minutes, hours, days, seasons, and years. This profile becomes even more complex near Earth's magnetic poles, where the nearly vertical alignment and intensity of Earth's magnetic field can cause physical effects like auroral. The ionosphere is traditionally very difficult to measure. Balloons cannot reach it because the air is too thin, but satellites cannot orbit there because the air is still too thick. Hence, most experiments on the ionosphere give only small pieces of information. HAARP approaches the study of the ionosphere by following in the footsteps of an ionospheric eater called ASCAT near Tromsø, Norway. There, scientists pioneered exploration of the ionosphere by perturbing it with radio waves in the 2 Euro-10 MHz range, and studying how the ionosphere reacts. HAARP performs the same functions but with more power and a more flexible and agile HF beam. Some of the main scientific findings from HAARP include, generating very low-frequency radio waves by modulated heating of the auroral electrojet, useful because generating VLF waves ordinarily requires gigantic antennas, generating weak luminous glow from absorbing HAARP's signal, generating extremely low-frequency waves in the 0.1 Hz range. These are next to impossible to produce any other way, because the length of a transmit antenna is dictated by the wavelength of the signal it must emit. Generating Whistler mode VLF signals that enter the magnetosphere and propagate to the other hemisphere, interacting with Van Allen radiation belt particles along the way, VLF remote sensing of the heated ionosphere. Research at the HAARP includes, plasma line observations, stimulated electron emission observations, gyrofrequency heating research, spread-F observations, high-velocity trace runs, airglow observations, heating-induced scintillation observations, VLF and ELF generation observations, radio observations of meteors. Polar mesospheric summer echoes have been studied, probing the mesosphere using the IRI as a powerful radar, and with a 28 MHz radar, and 2 VHF radars at 49 MHz and 139 MHz. The presence of multiple radars spanning both HF and VHF bands allows scientists to make comparative measurements that may someday lead to an understanding of the processes that form these elusive phenomena. Research into extraterrestrial HF radar echoes, the Lunar Echo Experiment. Testing of spread spectrum transmitters, meteor shower impacts on the ionosphere, response and recovery of the ionosphere from solar flares and geomagnetic storms. The effect of ionospheric disturbances on GPS satellite signal quality, producing high-density plasma clouds in Earth's upper atmosphere. Research done at the HAARP facility has allowed the U.S. military to perfect communications with its fleet of submarines by sending radio signals over long distances. Instrumentation and Operation. The main instrument at HAARP Station is the Ionospheric Research Instrument. This is a high-power, high-frequency phased array radio transmitter with a set of 180 antennas, disposed in an array of 12x15 units that occupy a rectangle of about 33 acres. The IRI is used to temporarily energize a small portion of the ionosphere. The study of these disturbed volumes yields important information for understanding natural ionospheric processes. During active ionospheric research, the signal generated by the transmitter system is delivered to the antenna array and transmitted in an upward direction. At an altitude between 70 to 350 km, the signal is partially absorbed in a small volume several tens of kilometers in diameter and a few meters thick over the IRI. The intensity of the HF signal in the ionosphere is less than 3 AA microwatt mass squared, tens of thousands of times less than the Sun's natural electromagnetic radiation reaching the Earth and hundreds of times less than even the normal random variations in intensity of the Sun's natural ultraviolet energy which creates the ionosphere. The small effects that are produced, however, can be observed with the sensitive scientific instruments installed at the HAARP station, and these observations can provide information about the dynamics of plasmas and insight into the processes of solar-terrestrial interactions. Each antenna element consists of a cross-dipole that can be polarized for linear, ordinary mode, or extraordinary mode transmission and reception. Each part of the two-section cross-dipoles are individually fed from a specially designed, custom-built transmitter, that operates at very low distortion levels. The effective radiated power of the IRI is limited by more than a factor of 10 at its lower operating frequencies. Much of this is due to higher antenna losses and a less efficient antenna pattern. The IRI can transmit between 2.7 and 10 MHz, a frequency range that lies above the AM radio broadcast band and well below citizens' band frequency allocations. The HAARP station is licensed to transmit only in certain segments of this frequency range, however. When the IRI is transmitting, the bandwidth of the transmitted signal is 100 kHz or less. The IRI can transmit in continuous waves or in pulses as short as 10 microseconds. CW transmission is generally used for ionospheric modification, while transmission in short pulses frequently repeated is used as a radar system. Researchers can run experiments that use both modes of transmission, first modifying the ionosphere for a predetermined amount of time, then measuring the decay of modification effects with pulse transmissions. There are other geophysical instruments for research at the station. Some of them are a fluxgate magnetometer built by the University of Alaska Fairbanks Geophysical Institute, available to chart variations in the Earth's magnetic field. Rapid and sharp changes of it may indicate a geomagnetic storm. A digisonde that provides ionospheric profiles, allowing scientists to choose appropriate frequencies for IRI operation. The HAARP makes current and historic digisonde information available online. An induction magnetometer, provided by the University of Tokyo, that measures the changing geomagnetic field in the ultra-low frequency range of 0–5 Hz. The station is powered by a set of 5 2500 kW generators being driven by M20-645 E4 diesel locomotive engines. Site: the project site is north of Gakona, Alaska, just west of Wrangell St. Elias National Park. An environmental impact statement led to permission for an array of up to 180 antennas to be erected. The HAARP has been constructed at the previous site of an over-the-horizon radar installation. A large structure, built to house the OTH, now houses the HAARP control room, kitchen, and offices. Several other small structures house various instruments. The HAARP site has been constructed in 3 distinct phases. The developmental prototype had 18 antenna elements, organized in 3 columns by 6 rows. It was fed with a total of 360 kilowatts combined transmitter output power. The DP transmitted just enough power for the most basic of ionospheric testing. The full developmental prototype had 48 antenna units arrayed in 6 columns by 8 rows, with 960 kilowatt of transmitter power. It was fairly comparable to other ionospheric heating facilities. This was used for a number of successful scientific experiments and ionospheric exploration campaigns over the years. The final IRI is the final build of the IRI. It has 180 antenna units, organized in 15 columns by 12 rows, yielding a theoretical maximum gain of 31 decibel. A total of 3.6 EMW of transmitter power will feed it, but the power is focused in the upward direction by the geometry of the large phased array of antennas, which allow the antennas to work together in controlling the direction. As of March 2007, all the antennas were in place, the final phase was completed and the antenna array was undergoing testing aimed at fine-tuning its performance to comply with safety requirements required by regulatory agencies. The facility officially began full operations in its final 3.6 MW transmitter power completed status in the summer of 2007, yielding an effective radiated power of 5.1 gigawatts or 97.1 dBW at maximum output. However, the site typically operates at a fraction of that value due to the lower antenna gain exhibited at standard operational frequencies. Related facilities: in America, there are two related ionospheric heating facilities, the HIPAS, near Fairbanks, Alaska, which was dismantled in 2009, and one at the Arecibo Observatory in Puerto Rico. The European Incoherent Scatter Scientific Association operates an ionospheric heating facility, capable of transmitting over 1 GW effective radiated power, near Tromsø, Norway. Russia has the Shura ionospheric heating facility, in Vasilsursk near Nizhny Novgorod, capable of transmitting 190 MWERP. Conspiracy theories. HAARP is the subject of numerous conspiracy theories. Various individuals have speculated hidden motives and capabilities to the project. For example, Rosalie Patel warned in 1996 for the deployment of HAARP as a military weapon. Michel Kosudnovsky stated in a book published by the Committee on Monetary and Economic Reform that recent scientific evidence suggests that HAARP is fully operational and has the ability of triggering floods, droughts, hurricanes and earthquakes. Over time, HAARP has been blamed for triggering catastrophes such as floods, droughts, hurricanes, thunderstorms, earthquakes in Iran, Pakistan, Haiti, Turkey, Greece and the Philippines, major power outages, the downing of TWA Flight 800, Gulf War Syndrome, and chronic fatigue syndrome. Allegations include the following: a Russian military journal wrote that ionospheric testing would trigger a cascade of electrons that could flip Earth's magnetic poles. The European Parliament and the Alaska State Legislature held hearings about HAARP, the former citing environmental concerns. Nick Bajaj Jr., the son of former U.S. Representative Nick Bajaj and author of Angels Don't Play This HAARP, has claimed that HAARP could trigger earthquakes and turn the upper atmosphere into a giant lens so that the sky would literally appear to burn, and maintains a website that claims HAARP is a mind control device. Former governor of Minnesota and noted conspiracy theorist Jesse Ventura questioned whether the government is using the site to manipulate the weather or to bombard people with mind-controlling radio waves. An Air Force spokeswoman said Ventura made an official request to visit the research station but was rejected. He and his crew showed up at HAARP anyway and were denied access. Physicist Bernard Eastlund claimed that HAARP includes technology based on his own patents that has the capability to modify weather and neutralize satellites. Stanford University professor Umra Ninnan told Popular Science that weather control conspiracy theories were completely uninformed, explaining that a theory unregistered trademark S absolutely nothing we can do to disturb the Earth unregistered trademark S, weather systems. Even though the power HAARP radiates is very large, unregistered trademark S minuscule compared with the power of a lightning flash and there are 50 to 100 lightning flashes every second. HAARP unregistered trademark S intensity is very small. Computer scientist David Nadich characterizes HAARP as a magnet for conspiracy theorists, saying that HAARP attracts their attention because its purpose seems deeply mysterious to the scientifically uninformed. Journalist Sharon Weinberger called HAARP the Moby Dick of conspiracy theories, and said the popularity of conspiracy theories often overshadows the benefits HAARP may provide to the scientific community. Austin Baird, writing in the Alaska Dispatch, said, "What makes HAARP susceptible to conspiracy criticism is simple. The facility doesn't open its doors in the same way as other federally funded research facilities around the country, and it doesn't go to great efforts to explain the importance of its research to the public." In 2009, the first episode of the television show Conspiracy Theory, aired by TRU-TV, HAARP was linked to the 2004 tsunami that hit Indonesia. Some have linked HAARP to the 2010 Chile earthquake. In popular culture, HAARP has been dramatized in popular culture by Marvel Comics, in the Tom Clancy's Net 4 series, and The X-Files. A fictionalized HAARP was the setting for a stage in the X-Men Legends game. HAARP was featured in the animated series G.I. Joe, Resolute, and in the first episode of Conspiracy Theory with Jesse Ventura. The alternative rock band Muse named a live album after this facility. HAARP's various antennas also inspired the set design for the performance, which was recorded live at Wembley Stadium. The plot of Craig Baldwin's 1999 film Spectres of the Spectrum revolved around a futuristic war machine inspired by HAARP. Topps, a trading card manufacturer, included a HAARP card in its 2013 Allen and Ginter trading card set. The card was featured in a subset of card titled Curious Cases. Shutdown: HAARP was shut down in early May 2013, awaiting a change between contractors who operate the facility. According to HAARP Program Manager James Keeney, Defense Advanced Research Projects Agency is expected on site as a client to finish up some research in fall 2013 and winter 2014. The temporary shutdown was described as being due to a contractor regime change. The Alaska Native Corporation AHTNA, Incorporated is reportedly in talks to take over the facility administration contract from Marsh Creek, LLC. In May 2014, it was announced that the HAARP program would be shut down later in the year. See also, Ionospheric Reflection, ASCAT, HIPAS, Poker Flat Research Range, Superdan, Shura Ionospheric Heating Facility, Weather Modification, References. Further reading, Y. Zaitsov. From Radio Telescopes to Electromagnetic Weapons. RIA Novosti. Retrieved September 27, 2009. Evidence for precipitation of energetic particles by ionospheric heating transmissions. National Geophysical Data Center. December 7, 2004. Retrieved September 27, 2009. J. E. Smith. HAARP completed. In Bay. Retrieved September 27, 2009. USNN and T.F. Bell. Polar Aeronomy and Radio Science, ULF-VLF Project. Star Laboratory, Stanford University. Retrieved September 27, 2009. USNN, M. Gokowski, D. L. Carpenter, N. Riddell, R. C. Moore, T. F. Bell, E. Pascal, P. Cossey, E. Kennedy, and S. Z. Meth. Multi-hop Whistler mode ELF-VLF signals and triggered emissions excited by the HAARP-HF heater. Geophysical Research Letters 31, L24805. Bibcode, 2004 Auroral 31248005 IDOI, 10.1029/2004 gallons 021647 E. J. Kennedy, P. Rodriguez, and C. A. Selcher. The High Frequency Active Auroral Research Program. Retrieved September 27, 2009. H. L. Rowland. Simulations of ELF radiation generated by heating the high-latitude D region. Naval Research Laboratory, Plasma Physics Division, Beam Physics Branch. Retrieved September 27, 2009. Donald Clare N7MGT, Secret Death Ray, or is HAARP a useful science tool? 73 Magazine, 14 a euro 17, 37, retrieved December 21, 2011 a first-person account from an amateur radio operator who got a full tour of the HAARP site. Patents, C.W. Hansel. Communication system by pulses through the Earth, U.S. patent 2,389,432. R.L. Tanner. Extremely low-frequency antenna, U.S. patent 3,215,937. G.F. Lydorf. Antenna near-field coupling system, U.S. patent 3,278,937. B.J. Eastlund. Method and apparatus for altering a region in the Earth's atmosphere, ionosphere, and/or magnetosphere, U.S. patent 4,686,605. B.J. Eastlund. Method for producing a shell of relativistic particles at an altitude above the Earth's surface, U.S. patent 5,038,664. External links, official website, HAARP at eastlandscience.com, a Euro website of Bernard Eastlund Scientific Enterprises Corporation. HAARP Executive Summary, Google Maps satellite image of HAARP, HAARP a Euro THTH 1/2 TH cubed TH micron THN THTH degree THTH 1/4 TH 3/4 THTHN